Why do top AI labs keep returning to a failed idea? Energy-based models were once the holy grail of generative AI, only to be abandoned for easier alternatives. But now, they're making a shocking comeback. In this video, we'll decode the physics of AI, how models treat data as valleys in an energy landscape, why calculating probabilities is mathematically impossible, and how EBMs are quietly solving the hardest problems in machine learning that diffusion models can't touch. If you think you know generative AI, think again. We are going back to physics. Let's start with the core metaphor. In standard generative models, we try to output a probability for every pixel combination. It's messy. EBMs take a different approach. They assign a scalar energy value to any input. Think of it like a terrain map. Good data, like a clear photo of a cat, sits in a deep valley with low energy. Noise or random artifacts sit on high peaks with high energy. The core hypothesis is inverse: nature prefers low energy states. Probability is defined by the Boltzmann distribution, meaning lower energy states are exponentially more likely. This turns generation into a search problem. Instead of writing pixels one by one, the model is just looking for the deepest valleys in the landscape. So, why did we abandon this elegant theory? The partition function problem. To turn that energy value into a real probability, you need a normalization constant called z. Z requires integrating the energy over all possible data points. For an image, that space is effectively infinite. It's computationally intractable. You can't calculate the exact likelihood because you can't sum up every possible pixel arrangement in the universe. This intractability forced researchers to rely on approximations, making training EBMs incredibly unstable and slow compared to the rise of VAEs or GANs, which offered easier, approximate likelihoods. But here is the genius workaround: you don't need Z to train the model. We use algorithms like contrastive divergence. The gradient has two opposing terms. First, you pull the energy of real data down the hill. Second, you push the energy of generated samples up. By balancing these forces, the model learns the shape of the data distribution without ever calculating the true probability volume. Another method, score matching, compares the gradients of the log likelihood directly. This allows the network to learn the geometry of reality without getting bogged down by the impossible math of normalization. So, how do we actually generate new data? We use a process called Langevin Dynamics. Imagine a hiker in a foggy mountain range. The hiker adds random steps, noise, but always moves downhill, gradient. Over time, this stochastic process converges to the low-energy valleys. The model doesn't invent data from scratch, it finds it by navigating the energy landscape. By repeatedly adding noise and descending the gradient, the system settles into a state that matches the distribution of the training data. It's a continuous connection between the energy function's shape and the quality of the output. Here's the twist: diffusion models are essentially a specific type of EBM. In diffusion, we learn an energy function by predicting noise at each step. While diffusion models dominate image generation today, they require many iterative steps and are computationally heavy. EBMs offer a more flexible framework for domains where defining a diffusion process is difficult, like molecular dynamics or complex physical simulations. Understanding EBMs provides the theoretical foundation for understanding why diffusion models work so well. They are cousins in the same family of energy-based thinking. This isn't new science. The concept originated in statistical mechanics and was adapted into Boltzmann machines by Hinton and Ackley in the 80s. Early versions struggled because they couldn't scale to high-dimensional data like images. They were limited to small, grid-like structures. For decades, the field moved toward autoregressive models and GANs because they were easier to train. But the theoretical allure of EBMs never disappeared. It just waited for modern deep learning architectures and powerful GPUs to make the complex math tractable again. So, where do EBMs shine now? They excel in unsupervised learning and anomaly detection. Because EBMs learn a continuous energy landscape, they are incredibly good at identifying what is normal. If a data point has high energy, it's an outlier. This makes them perfect for security, medical imaging, and scientific discovery where defining a generative process is harder than defining a validity metric. They are also gaining traction in reinforcement learning, where the energy function can represent the cost of a state, guiding agents toward optimal behaviors without explicit rewards. Energy-based models remind us that sometimes, the failed ideas of the past hold the keys to the future. By treating data as physics, we gain a deeper, more flexible understanding of intelligence. They may not be the fastest way to make a cat picture, but they might be the most robust way to understand the world. Thanks for watching.